Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be looking at Chapter 6 on nonparametric methods to help us answer the question, what do we do when the assumptions of our normal-based statistical methods are not met? So in our one sample, two sample, and many sample tests where we use t-tests or analysis of variance, we have assumptions of normality, either in terms of the sampling distribution of the mean or the sampling distribution of the difference in means, or of the residuals, which are basically that our populations are normal. And if any of those assumptions aren't met, then we should be skeptical about the inference that those methods give us. And so in this chapter, we'll learn other strategies for making comparisons between groups when we don't meet our normality assumptions. So our learning objectives are to be able to select the appropriate procedure based on what assumptions are being met or what information we know about the problem at hand, to explain the reason for using one procedure over another, and finally to decide whether the medians between multiple populations are different. So in these methods, instead of using the mean, which is sensitive to skewness or outliers, we're going to use a more robust measurement, the median. Robust meaning it's not influenced greatly by what happens in the extreme tails of a distribution. And there's lots of learning outcomes that this chapter will help us meet, in particular to select the correct statistical procedure, to define hypotheses, to summarize data visually, numerically, and descriptively, using R always, identifying and explaining statistical methods, the assumptions and limitations, and finally to make evidence-based decisions. I'll break this chapter up into 3 or 4 videos, and in this first video we'll look at one sample tests. So nonparametric methods do not require the normality assumption of classical techniques. So when those normality assumptions are met for the ANOVA or t-tests, then those are the most powerful, meaning that when the alternative is true, we're most likely to reject the null hypothesis in favor of the alternative, thereby making that correct decision in the interesting case when the alternative is true. That's what it means to be most powerful. When the normality assumption is not met, then we shouldn't trust those methods and instead resort to nonparametric methods. And we'll talk about the strengths and weaknesses of these methods. In particular, I want to start off just by mentioning a point I'll emphasize later. Nonparametric methods are not to be seen as inferior to traditional normal-based classical statistical techniques. They are another strategy, and sometimes they are superior. So we'll see an example of that throughout this chapter. So let's start with the sign test the sign test for a test and a confidence interval for the population median. So a sign test assumes that you have a random sample from a population. That's it. It makes no assumption about the population shape. Right? The standard t-test provides inference on a population mean, and the sign test is going to provide this on the median. Right? So the median is the point that separates the population distribution into equal halves. It's the middle point if you were to rank order all the observations or all the values in a population. If the population frequency curve is symmetric, then the population median and the mean are identical, right? If they're symmetric, in which case the sign test will also provide inference on the population mean, though it'll be less powerful than the t-test. All right, so here's the idea behind, maybe I'll just point to these figures for a second. So in the right-hand plot, we have a symmetric distribution. The mean and median are equal. But on the left, we have a skewed distribution, and the mean is being influenced and pulled toward that long right tail. So the mean and median in this case are not equal. So when we conduct inference on the median, it's that middle value that we're concerned with. And of course, lots of data follow this right skew distribution. Incomes, lengths of things in biology, or sizes, weights of things in biology. There's tons of things that follow this right skew distribution. So this ends up being a very a method that can be used in many situations. So the idea behind the sign test is straightforward. So suppose you have a sample of size M. Okay, so that's the sample size drawn from the population. We're going to test. So here's a new Greek letter for us. It looks like a letter N, but it's the Greek letter eta, E-T-A. And so eta is going to stand for the median. So we're going to ask whether the population median is equal to a specific hypothesized value. Okay. And this is the sign test. Basically, we're going to divide our data into greater than the median and less than the median. And we're going to count up how many are greater or less than. So let S be the number of sampled observations above that null hypothesized value. If the null hypothesis is true, right, that eta naught is actually the true median, then we'd expect S, the number of observations above that value, to be a half. So we're going to have evidence to reject the null if we have an S that's very different from half of our sample size. So if S is greater than half, then that suggests that the true population median is greater than our hypothesized median. Otherwise, if it's much less than, that suggests it's going the other direction. Okay. So S has a binomial distribution when the null hypothesis is true, right? Sort of like flipping a coin. If the true median is eta naught, then this resorts to a coin flip. So we're flipping a coin. Probability of observing a value greater or less than the median is 1/2. And so this is equivalent to a binomial distribution where you draw a sample of size M, say you had 30 observations, and then you expect to get 15 heads and 15 tails, right? 15 greater than the median, 15 less than the median. So that's where all of this comes down to. So that's what this is describing. We're going to use this BSDA package, which gives us the code or the function for the sign test. Notice the capital letters here. And this will, just as Ttest gives us both the p-value for our hypothesis test and the confidence interval, we're going to get those two outputs for this as well. So let's look at an example of skewed data. This is an example we've seen in a previous chapter for one sample test. We probably saw this back in chapter 2. Recall we had an income distribution that was extremely skewed. So here are the data, and I've sorted these from biggest to from largest to smallest. That's in sorting using decreasing equals true. We've got these two huge values, 1,046, where the rest of them are, between 0 and 12, with most of them being around 5 or 6 or 7. So this is extremely, this part of the data looks basically pretty symmetric, and then we have two extreme outliers. All right, notice the median here is 7, but the mean is 100. So the mean is greater than all but one observation. Look at the standard deviation of 318. Okay. So some plots coming up of the data. This top plot is perhaps the most informative in my point of view. We have it's a histogram all the points, notice the scale goes out to 1,000, right? There's that one observation way out in the far right. There's another value in around 40, and then there's the rest of them all clumped near 0. If we were to test the normality assumptions of the data, first if we look at the normality of the data, we see extreme observations, and on the right is the bootstrap sampling distribution of the mean, and in the bottom we're asking whether the sampling distribution looks normal or not. The obvious answer is no. In this case, notice that we have these modes, these distinct peaks. This effectively is the number of resamples in each bootstrap sample, or sorry, the number of times that we observe the most extreme value, the 1,000, in our sample. So most of our samples do not include that most extreme value, but when we include it once, then we get a mean around 100. And if we include it twice, we get a mean around 200, and 3 times around 300. So this is really just showing us how influential that one observation is. So no, we do not trust that the normality assumption for a t-test is met. Therefore, a sign test is a reasonable alternative. All right, so here we're going to load in the BSDA library. If we look at the t-test results, let's look at the confidence interval. It goes from -100 to +300. That's where we think the true mean is likely to lie. That's a sort of a crazy number, or interval. It doesn't really make sense because we just have one observation that's totally influencing that result. If we look at the sign test, however, for where the median is, here's the confidence interval for the median, somewhere between 2 and 11. That seems quite reasonable with our data. We have a pretty small sample size. Our observed median was 7, and it goes from 2 to 11. So we don't have that extreme influence that an interval for the mean had, because the nonparametric method protected us against that extreme influence. Now, one thing to point out here is that in nonparametric methods, we are constrained to using the sample size we have. And so in this case, if I page back up to our data, we had 12 observations here. And so 1 out of 12 is basically the resolution that we have to compute things like p-values. So if I page back down for a moment, the output of the sign test gives us the confidence interval, and then it also gives 3 confidence intervals here at the bottom. And you can see that the second one, the interpolated confidence interval from 2.3 to 11.6, that's given here. Okay, so why do we have 3 of these output? It's because based on 1 in 12 and the way we calculate bounds for our confidence interval, we have discrete confidence levels that we can actually be computed directly from the data. For example, a lower achieved confidence interval of 85% goes between the observation we saw in our data, 5, to another observation we saw, 8. So it's those 2 bounds that we observed in our data that can give us an 85% confidence interval. If we expand those by 1 observation, so go from 5 down to 2 and go from 8 up to 12 in our data, then that next sized interval based on our observations grows to 96.1. Okay, so it's a little too big. We're looking for a 95% interval, but there's no because the nonparametric method relies on the data themselves and the ranks of the data, that is the order of the data, we can't get an exact 95% interval often with the data that we have. So there are some interpolated methods that basically take guesses between the data points that we observe to give us the correct confidence level interval. And so in this case, we get a 2.3, which is between 2 and 5, and 11.6 roughly, which is between 8 and 12. And if we use those two values as our bounds, that is the best guess we have for what a 95% interval would be. Okay. So in practice, we'll feel comfortable using the interpolated confidence interval. All right. Let's look at a second example. This is going to be the age of a person's first heart transplant. I believe we've seen these data before also. Here are their sorted ages in decreasing order. A lot of people right around 50 years old or mid-50s. We have one person who's pretty young at 33 and another one who's 64. So let's plot the data. There they are. This doesn't look too bad, right? It looks basically symmetric with one young person in the left tail. Okay. Yeah, it's a fairly small sample, so yeah, I would still go with roughly symmetric in this case. When we look at normality, we see that the data themselves are pretty close to normal with just one extreme observation on the left. The data themselves are a bit left skewed, and the sampling distribution is also a little left skewed. You can see the left tail is longer than the right tail. This systematic difference that the black curve is from the right to left is below the red and above the red and below the red and then slightly above the red indicates that skewness as well. This may not be that troubling in terms of doing analysis and trusting the tails of this distribution, but this is one of those cases where we can use an alternative method, the sign test, instead. Okay. So let's perform a test of whether the median equals 50 years old for the average age at first heart transplant. I'm going to scroll down and I'm running the t-test as a comparison. So here's the t-test of the age values with the mean equal to 50. This has a p-value of 0.64. So it's sort of consistent with the mean. You can see the confidence interval goes from 45 to 56. It's almost a 10, or it's a little bit over a 10-year range. It's 11-year range. And here is the test for the median equaling 50 years old. P-value of 0.54, so consistent with the t-test above. And here's the confidence interval for the median, 47 to 56. It's actually slightly narrower for the median than the t-test was for the mean. And that's in part because we have that one value to the left that's a bit of an outlier. It's influencing the standard deviation to be larger than it would without the outlier. So this is the sort of case that we like to see as statisticians. We had data that where the sampling distribution of the mean is pretty close to normal, and we're testing a hypothesis of the mean being equal to 50 or median equal to 50. And in this case, there isn't a great difference between the sampling distribution being normal or not. And so when we test whether that assumption of normality makes a difference or not, right? So in the t-test we assume normality, we draw this conclusion that 50 is consistent with the data. And when we do not assume normality and perform the test, we get the same result. This is satisfying for us. It means that our conclusion was not based on the method that we used. There will be cases where we will get disagreement between doing a t-test and a non-parametric test, and in which case your conclusions do depend on the test that you conduct, and therefore depend on the assumptions that go into those tests, right? So that's what we are thinking about in this chapter as statisticians. All right. Let's look at one other strategy. So the sign test is pretty coarse, right? You set your median, and then you're just looking at greater than or less than, and you're counting up the values using the binomial distribution. We're not taking into account any information about how far you are from the median. So the Wilcoxon sign rank test helps have some sensitivity to how far you are from the median. Effectively, rather than just saying greater than or less than, we're going to rank our data and then change the values of our data from the actual values that they are into the ranks. Okay, so if you are the minimum value in a data set, your value is now the number 1, because rank-wise, you're the first observation. And if you are the nth, most extreme, greatest value, then your value goes from being, in that income example, instead of being 1,000, you're going to be the number 12. I think there were 12 observations. So your data become ranks, and then all the calculations are computed on the ranks. Okay. It's not quite exactly the same as using the ranks in a t-test, but it's not far from that. All right. So the Wilcoxon sign rank procedure is the method we're going to use. It's going to assume that you have a random sample and you have a symmetric frequency curve or distribution. Okay, so the curve doesn't need to be normal, but it does need to be symmetric to use this procedure. And the test in the confidence interval can be viewed as either for the median or the mean, because symmetric means that the mean and the median are going to be the same. All right, so let's illustrate this on a very small example. So this first column of 8 numbers are the actual data values, and let's walk through the ideas here. So to illustrate the computation, the Wilcoxon sign rank test has a statistic called W, and we're going to test the hypothesis. So we're going to compute the statistic. That's all I'm saying. The null hypothesis here is that the mean or the median equals 10. And we want to test whether 10 is a reasonable value for the mean or median. So the first thing we're going to do is we've got our data in this first column. In the second column, we're going to subtract the hypothesized mean or median from that data value. So 10 was the hypothesized value, 20 minus 10 is 10, 18 minus 10 is 8, and so on. Some of these values become positive and negative. You can see that there's 6 positive and 2 negative values. Here's the sign of each of those values, and here's the absolute value of those differences that we computed. Now we're going to go into the rank. Okay, so we have the sign of these values. Now we're going to rank these absolute values from the hypothesized median. Effectively, we're going to compute the distance of each value from the hypothesized median and rank those distances from the median. So the smallest distance here is a 2, so it has a rank of 1. The second smallest value is a 4, it gets a rank of 2. 5 is the third one. And then we have 2 8s. We have an 8 down here, we have an 8 down here. And so those would take ranks 4 and 5, but because they're tied, they get the average of the ranks. So instead of 4 for one and 5 for the other, we have 4.5 for both. So this is one strategy for dealing with ties. Then we have the 6th, 7th, and the most extreme one, 13, is rank 8. Finally, we apply the sign that we calculated here to the last column by multiplying it by the rank. So we have a -3 and a -1. The rest are all positive. Finally, the statistic that we're computing are going to just add up all the positive values. It's equivalent if you add up all the negative values. It doesn't really matter. This gives us a statistic of 32. Fine. Then we need to compare 32 to a distribution under the null hypothesis that the true hypothesized value is actually equal to 10. Okay. So the way to think about this is about what is the sum of all the ranks. So the sum of ranks is going to be m times m plus 1, where m is the sample size. So if we've got 8, that's going to be 8 times 9. So this is the sum of all the ranks, right? So, and times 1/2. So if m is 8 plus 1, that's 8 plus, well, I'm going to divide by 1/2 too. Okay, so I'm going to do 4 times 9, which is 36. So that is the total of the ranks. And if about half the ranks are to the left and half are to the right of our hypothesized values, then that means these signs should be roughly distributed among these ranks. And so our test statistic W is expected to be half of the total number of the ranks. Okay, so instead of 36, we're looking at an 18. So we want to know, is our 32 that we observed close to 18? Okay, so then we plug that into, we let R figure this out for us. There's ways of computing this, this distance under the null hypothesis, and that will be computed in the Wilcox.Test function to calculate our p-value or to get a confidence interval. So here's our made-up data. Here's the values in decreasing order. And let's take a look at a plot of the data. Fairly flat. We only have 8 observations, but here's 10 on the left-hand side, so we definitely have more data on the right. We have this a little bit left skewness, as we can see in the box plot. When we plot the data themselves do not have strong deviations from normality, though, you know, we do have only 8 observations. You can see how wide these error bars are, reflecting that uncertainty. And here in the bottom right is the bootstrap sampling distribution of the mean, somewhat normal. So I would probably feel pretty comfortable doing a t-test in this case. But let's see what the Wilcox does compared to that p-value, or t-test. So here's the t-test with assuming that mu equals 10. We have a p-value of 0.035, so it's less than 0.05. We'd reject the null in favor of the alternative that the mean is not equal to 10. For the Wilcox test, okay, we have mu equals 10. We do, if we want to get a confidence interval, need to specify that we do want the confidence interval, so confidence interval dot true or equals true. And notice we have some warnings. This is not a big deal. Because we have ties for our ranks, which we saw in the table above, this the method can't compute an exact p-value. Exact p-values are only defined for data where there are no ties. In this case, it's not a big deal. It will give us a test that allows calculation of the p-value and the confidence interval with continuity correction. It'll be just fine. So here's the result. 0.058 is the p-value. It's greater than 0.05. Therefore, we fail to reject the null. The data is consistent with a median or mean equal to 10. And if we don't use the continuity correction, here's the p-value, 0.0496. Therefore, we would reject the null hypothesis. Okay, so this often puts people in an uncomfortable situation. So here are 3 tests that we just did on the same data with slightly different assumptions, right? The t-test assumes that the sampling distribution is normal. We rejected the null, and in favor of the alternative. And the Wilcox test we ran in 2 different ways. One was to use something I call a continuity correction, which uses a normal approximation for the p-value. And the second test we did not use the continuity correction. And those 2 methods themselves have different conclusions, right? One is greater than 0.05, one's less than 0.05. So a point that Andrew Gelman makes over and over again in his writing is that the difference between a statistically significant result and a non-significant result itself is not significant. What I'm saying is that the difference between this p-value that's slightly greater than 0.05 and this value that's slightly less than 0.05 is not statistically different. There'd be no way to identify differences between values so small, right? We're on an edge case, or not an edge case, but a sort of a pivotal case where we just happen to be close to 0.05 and one's slightly greater and one's slightly less than. Okay, so what decision should you make? Well, my recommendation here is to think hard about what model assumptions were, right? We assume normality assumption with the t-test. Is that reasonably met or not? And if you thought it was reasonably met before you saw the result of the test, that is, you're not changing your conclusion based on what the test said, then you can go with the t-test. If you felt that the assumption was not really met, then you were going to use a Wilcox test. So this is a moment where you probably want to go and learn more about this continuity correction and see what makes sense. The default for this method for Wilcox test is to perform the continuity correction. Notice I didn't specify any additional arguments up here about the correction, and it performs it automatically. And it may be the more conservative method. For example, the p-value is a little bit greater. I might go along with this Wilcoxon with the continuity correction in this case. Okay, if there was strong reasons to not use a continuity correction, then this was your conclusion. But maybe think about this. This p-value is 0.04967. That's basically 0.05, right? And so at the end of the day, you may want to say, well, if I'm really using 0.05 as my decision point, this is so close to 0.05, it feels like I don't have a definitive answer. And maybe the thing to do in this case is to go out into the world and collect another set of samples to help clarify whether the null is to be supported or rejected from the data. Okay, these are hard decisions to make. All right, let me stop here. I'll come back and talk about paired data, and then we'll go on to two sample tests and many sample tests.